So welcome to video problem 16. In this problem we will use Biot-Savart's law to determine the magnetic flux density, which is the B field at the center of a square steady current loop located in free space. So you can see the configuration of a square conductor here. It carries a current I, which is positive and flows in the direction indicated on this figure. It has a side length which is equal to A, and it is residing in free space with free space permeability mu0. We introduce a rectangular coordinate system in the way shown in this figure, so that the observation point is actually equal to 0.0.0. So that is the observation point here at the center of the loop. Obviously, the loop will result in a rather complicated field dependence, and we can not identify any current enclosing path on which, for instance, the tangential component of the B field will be constant, and that will prevent us of using Ampere's law, which requires symmetry to find the B field in this particular case. We will have to resort to Biot-Savart's law, which is shown in the expression to the right. So this is the top view of the configuration. We have the rectangular loop located in XY plane, and the Z-axis will point towards you at this particular point here. We have the loop as being composed of four conductors. One conductor is shown here, another one is shown here, another one is shown here, and another one is shown there. The side length of these conductors is equal to A, and we can recall from video problem 14 that we have considered such conductors and actually determined the field at a radial distance r from the origin of these conductors. Consult video problem 14, where you will see that this was the field we determined in that particular case. And we will simply use this result, adapt it to our coordinate system here, and exploit the superposition principle, where we will actually add the fields due to these four side lengths. Obviously, if we consider this side length over here, what we see is that L from this expression here is A divided with 2. The distance from this conductor here to the observation point is equal to A divided with 2, and our phi unit vector that we can see here, when evaluated at this point for this particular side of the loop, will point in the Z direction. So very easily you see that for this side of the loop you get the field which is given by the expression here, and you simply have to superimpose four of those fields to get this final result that we can see here. So this is actually a simple expression for the B field at the center of this square current loop, which we obtained on the basis of some previous results and also the superposition principle. We have essentially decomposed the square loop into four linear conductors. So we are done essentially with our assignment here, and we would like you to verify the above expression with regard to the units on both sides, and also try to determine the B field at a point along the Z-axis using Biot-Savart's law for this particular loop. Thank you very much for your attention.